So lesson 9.4, we are going to look at quadratics, so these equations that form parabolas, but specifically at how quadratics and projectiles are related. So what's a projectile? So we'll get to that in a second. The big idea says assuming constant gravity, so we can assume that here on Earth, both the path of the projectile and the height of a projectile over time can be described with this equation that we've been looking at the first half of chapter 9 here. Ax squared plus bx plus c when a is not 0. So this equation that we've been working with that forms a parabola on our graph. We talked about a, b, and c being numbers. They're coefficients to x squared and to x, and then a number that's by itself. And we talked about how this is an intercept. All right, and so we're going to specifically look at how this equation can be used to find the height of projectiles. So a projectile can be defined as an object that is thrown, dropped, or launched and then proceeds with no additional force. So I think we've heard of projectiles before. So it could be a baseball being hit, it could be something being shot out of a gun, it could be something thrown or dropped. Okay, and there's a general formula that we're going to use for this. And it's going to look similar to one of the formulas that we've used before because gravity is involved. And so we've already used equations where objects are dropped and we talk about how far it's gone. And so there was that coefficient of 16, which has relation to gravity, and that's why things fall at certain rates. And so this equation is going to say negative 16 t squared plus v times t. So v is going to be our b, and we'll define v in a second, plus h. Now, this 16 is talking about feet. Okay, so if our question is specifically talking about measurements in feet, then this is the equation. But we need to be able to go back and forth between meters and feet because there's going to be questions where things are in meters in the metric system. And so if the question is given in meters and that's what we're working on, then this number right here, and this you could think of as a negative 16, is going to be negative 4.9. These are equivalent to each other. It's the same measurement, but just in different units. So 16 feet is the same as 4.9 meters, approximately. It's rounded. Okay, so we would substitute in the negative 4.9 for the negative 16 if this question was specifically talking about things in meters instead of feet. So the initial height or anything like that that's given in meters would be negative 4.9 for the pull of gravity on it. So let's define everything else. And actually, I want to make one small change. We're going to put this little subscript here of 0. And very often, you'll see it here, and so I don't want you to be confused. And that little subscript of 0 has to do with the initial something, so what you started with. So this h and this h are different. This h is the height that the projectile is at currently that we're going to find. This h is where it started. That's the initial height. So h is clearly the height, and that's what we're solving for. The negative 16 or negative 4.9, that has to do with gravity. T equals time, and that's going to be in seconds. And here's the important ones. These two numbers right here. These are the ones we're going to be substituting in. V with this little subscript here. This is the initial velocity. The way to think about that is the beginning velocity. Something takes off out of a gun at this velocity. It slows down over time. Okay, but this is the initial velocity. And this right here, let's say something is dropped from the top of a building. We can measure where the height is at certain times, and that's this h. This h with the subscript 0 there, that's telling you that's the initial height or the starting height. And so it's important to be able to tell the difference between all of these. So when you see that subscript there, that means that's what you started with, or the initial velocity or initial height. All right, so we're basically just going to work all of our questions today around this equation to make sure that we can go in and out of it and use it to solve for stuff. So let's look at example number 1. A ball is launched from initial height of 6 feet. So there you go, initial height of 6 feet with an initial velocity of 32 feet per second. So we've got some numbers to plug in, and we specifically are going to have to choose between two equations. So I do want to go back up here and just make sure that we clearly understand that we can make this equation look like this. So it's going to look exactly the same. Okay, nothing's changed in this equation except the negative 16 to negative 4.9. So this is in meters, and this is in feet. And so one of the things we have to do is as soon as we start looking at these questions, we have to see what kind of units the question is giving us and then use the right form of the equation. They're the same, okay, but they're just in different forms with different units. So we're just going to write the equation describing the height, h, in feet of the ball after t seconds. Okay, after t seconds. So we don't know how much time has passed, but we do know some of these things. So this equation will help us find the height. We don't have that yet. Since this is in feet, I'm going to use the negative 16. I don't know the time that's passed yet, so I'm setting an equation that if I knew the number of seconds that it's been already projected, what would the height be? And so I'm just going to put t squared there. I don't know what t is. Plus my initial velocity of 32 times t, so times the number of seconds, plus my starting height, or my initial height, which was 6 feet. So this is my equation right here. So what this equation will give me is the height of this object, or this ball, after a certain number of seconds. So real quick, let's get a visual of this so we understand kind of what's going on and why we're using this equation. So negative 16x squared plus 32x plus 6. Let's go ahead and take a look at our graph. What does this look like? And so we probably want to zoom out here just so we can get a better view of it. All right, and we could adjust our window to get something better, but you can see that this is an upside down parabola. And when we're talking about these negatives, that's not really going to be negatives, right? There's going to be a ground here, and so the ball is not going to fall below ground. I guess there could be a circumstance where that could happen. But just in general, we're just looking at height of 0 being the ground. And so this is projected up. The ball is launched up. It's going to have a peak, and then it's going to come back down. And so you can see how this parabola, because of gravity, represents the height of the ball. It's shot up at a velocity. Eventually it slows down, and it comes back down to earth and hits the ground. So this parabola is going to represent the height of that ball being projected up. And so now we're going to go ahead and we're going to use the equation that we just built to solve for the height after a certain number of seconds. So how high is this ball going to be 2 seconds after it's thrown or projected up? So all I have to do is go ahead and take this equation and plug in 2 seconds for t. So h equals negative 16. Now notice this is t squared. This is going to be 2 squared. So I'm going to write it out so we're not confused. Times 2 squared. If you wanted to put it in parentheses squared, that's fine. But we need to make sure that we know that this is going to get squared before we multiply it. Plus 32 times t, so 2, plus 6. Okay, so now we just need to go ahead and we need to solve this. This is going to be, I mean, you could plug the whole thing in, but basically this 2 squared is going to be 4, and I want to re-emphasize that, so I'm going to go ahead and write that out. 32 times 2 is going to be 64. This multiplication needs to happen as well, so negative 16 times 4 is negative 64. Plus 64, so that's going to be 0, plus 6, which means my height is going to be 6, and this is in feet. This whole equation is in feet. So after 2 seconds, after it's thrown, is going to be 6 feet. Now, let's say you went to the table. Let's say you plug this in. You could go ahead and see that. So at 0, the initial, it was at 6, right? It was thrown up at 6 feet. After 1 second, it's 22 feet up in the air, and after 2 seconds, it's down to 6, and then it would be below ground at that point once it hits the negatives. So it would hit the ground in a normal circumstance. So how high would the ball be in 3 seconds? So we should be able to see here that it's going to get negative 42 if we run the equation. So we're going to show our work with the equation. So negative 16 times 3 squared now. So it's 3 seconds. We're putting 3 in for t, going back to the starting equation. 32 times 3 plus 6. So this is negative 16 times 3 squared is 9. Plus 32 times 3. I'm going to leave that for a second. Plus 6. All right, let's run the numbers here. So negative 16 times 9 is negative 144. 32 times 3 is going to be 96 plus 6. And so if we run this all the way across, negative 144 plus 96 plus 6, h equals negative 42, which again we could have found in our table because we plugged in this initial equation into our calculator, and there's your negative 42. Now, if this was actually talking about a regular circumstance, you wouldn't say the height is negative 42 feet. You would say the ball is on the ground. Okay, if it's in any negative number or 0, that means it's now hit the ground. Okay, of course, there could be some circumstance where there's a hole in the ground and it could go farther down, sure. Okay, but for just a regular old circumstance here, we're going to say if it's negative or 0, the ball has now hit the ground. Okay, so pretty basic, really. It kind of follows along with all the stuff we've been doing. It's just now basically taking a word problem and applying it to this. So let's go ahead and look at this in meters. We want to make sure we can handle that. So in example number 2, your object is dropped from initial height of 90 meters. And we're not given an initial velocity. And the reason is because it's dropped. And so it's not sent, it's not thrown at a certain speed. And so our initial velocity is actually going to be 0. 0, because it's not taking off, it's not being shot out of a gun, it's just being dropped. So it has 0 speed when it's let go, and then it's obviously going to increase in speed as it's dropped. And so our initial height is 90 meters. So this is h0, but it's in meters. All right, and so we want to make sure when we grab the equations that we don't grab the one that's in feet. We're going to grab the one that's in meters. So it's going to be negative 4.9 that goes in the front. So h equals. So we're going to write the equation here after t seconds. So not plugging anything in yet, just using our initial velocity and our initial height. And so we're going to use negative 4.9 t squared plus, now our initial velocity, because it wasn't shot out of a gun or thrown at a certain speed, it was just let go of, is 0 times t. And so that's actually going to disappear because you're multiplying by 0. And then your initial height was 90. So we can simplify this. I don't want to leave it like this because we can get rid of this. And so a better formula here is negative 4.9 t squared. This goes away, plus 90. So basically you can see this is my starting height. This is my y-intercept. And then as time passes, gravity is pulling this down. And so there's a decrease. That's why it's negative. And so we can go ahead and use this equation. What's the height of the object after 1.5 seconds? We're just going to go ahead and plug it in. So negative 4.9. T is going to be 1.5 squared plus 90. Okay, you would run this in your calculator. You would do 1.5 squared. That number gets multiplied by negative 4.9. And then you add 90. I'm just going to go ahead and give you the answer. We know how to plug it in a calculator. Doesn't give us any rounding, so I'm going to write it out like this. And this is in meters, not feet. So same idea as example 1. I don't want to spend too much time, but we just need to make sure that we recognize when it's given in meters or it's given in in feet, then we need to make sure we choose the right number, either the negative 16 or the negative 4.9. All right, example number 3 now. We're not going to actually write the equation. We're just going to look at a graph, which we've done before, and try and pull the information off that we need. So it says refer to the graph. It shows the height in feet. Okay, we always want to make sure what units we're using of a soccer ball t seconds after it's drop kicked into the air. So it's kicked up into the air It's going to hit a certain height, a maximum, and then it's going to come back down. What is the initial height of the soccer ball before it's kicked? And so when you take a look, if we didn't have this labeled, you'd have to guess. But they tell you that this is a point on the graph. 0, which is your x, which is your time in seconds. So this is when it started. At 0, it's 2.5 feet above the ground. And that makes sense because they're drop kicking it. They're not kicking it off the ground. They're dropping it. So the height that it hits the person's foot when they're kicking it is 2.5 feet above the ground. So what's the approximate height of the soccer ball at 1 second? So we're going to go to 1 second right here and follow it up. And it's going to hit here. Now this is approximate. And so we're just kind of guessing. It looks a little higher than 65. And so since you're estimating and it's an approximate, there would be some leeway here in your answer. I'm going to say approximately 67 feet. But if you said 66 or 68 or something like that, that would be accepted. What is the greatest height the soccer ball reaches? So that would be the top. Now remember, the first number is your x, which is representing your time. So 2.5 is the time. Y is your height. Okay, and so that's the height that it reaches. And so it's 102.5 feet. And then if they said, how long did it take it to get to 100 or to its highest point, you would say 2.5 seconds. At what time is the soccer ball 38.5 feet high? So you can see right here, 38.5 represents the height. And so we can see it's at 4.5 seconds. That's what the X represents here, and you can follow it down, 4.5 seconds. But if you look closely, it hit that twice. Okay, so it's right here, and then it's also going to be right here, just underneath. So 38.5. It's going to hit it twice, as parabolas do. 38.5, if you put that line across, looks like that. And so this would be an estimate right here. This looks like approximately halfway, though, so about 0.5 seconds. So this one we know specifically is 4.5 because it's given to us. This one you'd have to estimate. Looks like about 0.5. You had the equation, you could go plug it in and you could figure it out. And then approximately how long is the ball in the air? So it's kicked, goes all the way up, it goes all the way down. It's in the air until it hits 0. So it looks like it's hitting 0 at about 5 seconds. All right, so that's just taking a look at how this shows up on the graph. And of course, there could be an equation for this that we could do more work with. But we want to make sure that we can write the equation, use the equation, and also look at a graph and analyze it.